Hello, everyone. I'm Chunwei from the University of Chicago. I'm glad to be here to share our recent work on float compression. It's called BUFF. BUFF is a fast and effective float compression. It's especially good for the float data with limited range and precision. Modern applications and systems are generating huge amount of data every day. It is expected that the amount of data generated in the future will continue to grow and largely be driven by IoT devices. A lot of this data is sensor data that is stored as a float format. Different applications have different requirements on the data precision. High precision is meaningful only if it matches its purpose. Take GPS coordinates as an example. As is shown in the picture, if you are trying to locate a building, 3 or 4 digital precision is good enough for your purpose. And if you are pointing out a city, 1 digital precision is good enough. Any additional precision is meaningless if it doesn't match your goal. Thus will be usually ignored. So many real-world datasets are usually with limited precision. In addition to limited precision, bounded range is another common feature for many datasets. There are basically 2 reasons for this. First, data is defined by sensor itself, as we can see from the right 2 figure. Any sensor, no matter how much it costs, it's always designed with limited measurement range and precision. Therefore, the data generated by those sensors is always associated with those 2 features. Second reason is many experiment targets are usually defined with clear physical range. For example, air humidity and CPU usage are defined between 0 and 100%. In order to meet a different range and precision requirement from the real world, float point is designed by floating the radius point to support a trade-off between range and precision. Float point is now widely used in many systems and applications. It's popular not only because it provides extended range and precision, but also it provides relatively high precision in most common used range around 0. However, many applications or datasets only span a fixed range with limited precision, which is a small subset of the broader range and precision provided by float in general. For example, NYC taxi dataset include a GPS data point in New York City area. So the latitude value is usually between 40.6 to 41.1 with 6 digital precision. A city temperature dataset usually includes the data value between -99 to +96 with 1 digital precision. However, this limited range and precision feature is barely used by any float compression approach in the past. There are basically 3 different types of lossless compression techniques for float. The first one is dedicated float compression. For example, Gorilla is the most popular one, widely used in many database systems, such as InfluxDB and TimescaleDB. Gorilla is a delta-like compression method. It calculates the XOR for adjacent values and only saves the difference part. The second type uses the integer compression technique for float. For example, Sprints. Sprints is a compression originally designed for the integer, but it can be extended to float as well. When using Sprints for float, it first scales the float number into integer, then apply Sprints compression on those integer numbers. The third class is the general purpose compression technique like gzip and snapping, where float numbers are converted into byte array and then apply those compression techniques. However, none of those compression methods leverage the limited range and precision information to improve the compression performance. Those 2 common features can help on the float compression if we use them properly. To begin with, we can leverage the bounded precision to compress the data. For example, for a given value 3.14, if we want to keep 2 decimal precision, we can remove some trillion bits while still able to approximate to the value with 2 places of precision. In general, different precision requires different number of bits. This lookup table helps to quickly decide how many bits needed for a given precision. So with limited precision, we can remove a lot of insignificant trillion bits while still guarantee the precision. Besides, with bounded range, we can offset the input value to save more bits. Basically, this is the motivation of buff. With bounded range and precision, we can reorganize the bit space to only focus on the target range for a given application, thus achieve better flow compression. Let's see how buff works. Given a value with 4-digit precision, we first check the lookup table. We know that 15 bits is good enough. Our first step is extracting integer part and fraction part by buff extractor with pure bit operations. You can find more detail about the extractor in our paper. Then, with the range information either given by user or detected by our encoder, we can offset the integer part by the minimal value to further condense the range space. Basically, this is the bits we need to save for the given dataset. The next problem is how to properly allocate those bits. We can save those bits as a whole into storage, or we can use a byte-oriented splitting, where we split those bits into byte and save in a column map. The byte-aligned format brings us good read and write speed and also better query performance. With a byte-oriented layout, we can apply progressive filtering. With a given predicate, we can translate this predicate into predicates on subcolumns with buff metadata information. After evaluating on the first subcolumn, we get a bit vector indicating the potential candidate entries. Then on the following column, we are able to skip to the targeted rows and only evaluate those corresponding entries. As more value processed, there are less record need to be checked. Progressive filtering is super efficient, especially for high selective queries. Buff query relies on byte operations, thus easy to deploy on simple hardware like IoT devices. However, when the buff compressed data is delivered to a more powerful edge server or cloud, buff can also use advanced hardware like SIMD to speed up the query. Buff's byte-oriented scrapping layout is well suitable for SIMD execution. The buff SIMD filtering runs similarly with what byte slice or bit weaving do on integers and what pits do on string values. So for buff SIMD filtering, we evaluate the first subcolumn in the unit of each SIMD word batch until the end, output the bit vector for the first subcolumn, and then repeat on the second subcolumn until the last column. Then for this equality filtering, we take the intersection of all the bit vector from different subcolumn and return as final result. SIMD is usually good on low selective filtering, where a large percentage of entry need to be evaluated, where progressive filtering is efficient on high selective queries, where a large percentage of record can be skipped. Based on this observation, we design adaptive filtering to leverage the benefits from both sides. In addition to faster filtering, buff also help to speed up some aggregation queries. You can find more detail in our paper. In our experiment, we pull data from a variety of domains and distributions. We also include benchmark evaluations. Here we show the overview of buff performance. We normalize the performance on each dimension between 1 and 10. Then we take the average across all the data sets. In the radar chart, alter is better. As we can see, buff outperform others in compression ratio, compression throughput, most queries and benchmark evaluations. If we take Gorilla as a baseline, buff achieve 2 to 3 times faster compression throughput, 10 times faster on average for filtering queries, 22 times faster on average for aggregation queries, 1.3 to 2 times faster for benchmark queries on TSBS and InfluxDB benchmarks. In our paper, you can find a detailed evaluation on each dimension shown in this radar chart. And also you can find more detail on how buff handle outliers, how to handle the AQP queries, and the variable precision materialization in our paper. Thanks.